Okay. Now we'll see the DSBSC first modulator, which we already completed, balanced modulator. Now we'll see the second DSBSC modulator, which is nothing but ring modulator. Okay. Now first we'll see the ring modulator circuit. Now here there are two center tap transformers which are used here. Now there are four diodes are used here. There are four diodes which are used and two center tap transformers. Now this is diode D1, this is diode D2. Now this is diode D3. Now this is diode D4. And the input is a message signal. And this is the two center tap transformers tapping here. Now this is the carrier signal. Now for easy operation of this circuit, I just use this carrier signal as a square wave. But actually this is a sinusoidal signal because all are sinusoidal modulation itself. But for easy calculations part, I just take this as a square wave. Okay. Now we'll see the operation. Okay. And what should be the output here? What is the output? Okay. Now we'll see one by one case. Now I just take case 1. Now this is the case 1 as when C of t is greater than 0, means positive polarity, positive cycle. C of t is greater than 0 means this one. Now when C of t is a greater than 0, this side. So this is a positive potential. When a positive potential is applied here, now this is the circuit. Now this is the positive potential, which means now diode D1 is on condition. Now diode D2 is also on condition. Now diode D3 and diode D4, because this is the positive is connected to cathode, this positive is also connected to cathode, then these two are the reverse bias. Now diode D1 and diode D2 is forward bias. Okay. Now diode D3 and D4 is reverse bias. So now this is a message signal M of T. Now what is the output? Now this is the output. Now directly the load sees directly source. So output which is equal to M of T. Can I write like this? Now this is the output which is equal to M of T. But this circuit operation is based on the carrier voltage. Okay. So this is the carrier voltage. Can I write like this? This is plus 1 volt. Now plus 1 volt means when C of T is greater than 0. So this is finally the output which is nothing but message signal is coming because of the carrier voltage. The diodes are fully under the controlling of carrier voltage. Okay. So this is M of T into C of T is a DSBSC signal itself when C of T is greater than 0. Now we will see in the negative half cycle also. Now case 2, when C of T is less than 0 means negative side. Okay, this side. Now this is the negative side. Therefore, now diode D1 and diode D2 is reverse bias, right? So now diode D3 on condition, D4 is also on condition. Now see here. Now diode D3 and diode D4 is on condition, and D1 D2 is open circuit. Now what is this output? Now output is there is a twist here. Okay, then it which is nothing but minus M of T. Now output which is equal to M of T into, can I write this is minus 1 volt? Yes. Therefore, now this is output which is equal to M of T. Now this is minus 1 volt because of the carrier voltage. So this is nothing but a DSBSC signal or not? Yes, this is a DS message and carrier. Message and carrier is multiplied. Now which is nothing but a DSBSC signal. Now this is a ring modulator, and students are asking that why this is a ring modulator. Now why this is a ring modulator? Now see here. Let us assume all these diodes are in on condition. So if all these diodes are in on condition, now see here. This is on, right? This is on, right? Now see here. Now this is also on condition. Now this is also on condition. Now if all the diodes are in on condition, now this is a twist. Then this is nothing but a ring or not? This is a ring formation, right? This line. All diodes are on condition. Now this diode, this diode circuit operation will form a ring. Therefore, but all diodes are on or off, that depends upon the anode and cathode voltage. But all diodes are on. Now it will form a ring. Therefore, this is called as a ring modulator. Okay. Now first you take this one and we'll Now this is the message signal. Now I just save. Now this is a carrier signal. Now the modulated signal is now see here. Now when the message signal is crossing the negative polarities, now there is a phase shift here, right? Now see here, in DSBSC, when the message signal is crossing this negative polarity, when the message signal is crossing the zero axis, now there is a phase shift. Okay, now there is a phase shift of 180 degrees. Now in DSBSC, there is a phase shift of 180 degrees when m of t crosses the negative side. There is a phase shift of 180 degrees when m of t changes the polarities, means positive side to negative side. Practically, sinusoidal signal is used as carrier. Practically, sinusoidal signal is used as a carrier signal because it is having only one frequency. But any other periodical signal will have infinite harmonics. And ring modulator is not used practically because cost and complexity is high. Cost and complexity is very high because of two center tap transformers. Now, these are the DSBSC modulators, which is nothing but the ring modulator. Okay. So there are two center tap transformers which are costly and cost increases, and hardware complexity is also very high. Now that's why the most of the practical application for generating DSBSC balanced modulator is used, because that is available directly in IC's form. Okay. So that's why it is not used practically. Okay, no doubt. Now, classroom workbook question number 17. Now, what is the question number 17 is, a DSBSC signal is generated. A DSBSC signal is generated by using a nonlinear system as shown in figure. A DSBSC signal is generated by using a nonlinear system as shown in the figure below. Now, a nonlinear system as shown in the figure below where V naught equal to A into Vi plus B into Vi cube, where V naught equal to A into Vi plus B into Vi cube, where Vi is m of t plus cos 2 pi fc, where Vi is m of t plus cos 2 pi f1 into f1 into. Now what is the question is, the output of the system, nonlinear system, a DSBSC signal. Now see the question. A DSBSC signal is generated by using a nonlinear system. The output of the system is passing through a band pass filter to select a DSBSC signal with a carrier frequency of 1 megahertz. Okay. So the output of the system is passing through a band pass filter to select the DSBSC signal. Determine the value of f1 so that what is asking is determine the value of f1 such that carrier frequency of DSBSC signal is 1 megahertz. Okay, this is the question of finally. Okay, then you understand the question or not? First, a nonlinear system as shown in the figure below to generate a DSBSC signal. Now the nonlinear system is passed through a band pass filter to select a DSBSC signal. Now determine the value of f1 so that the carrier frequency of DSBSC signal should be 1 megahertz. Okay, Vi is given, V naught is given, everything is given. So now we'll find V naught. What is V naught? V naught, which is equal to A into Vi. What is Vi? A into m of t plus A into cos 2 pi f1 into t plus B into Vi cube. B into Vi cube is A plus B whole cube, A cube plus B cube, B into cos cube 2 pi f1 into t, A cube plus B cube plus 3A square B, B into 3 m square of t into cos 2 pi f1 into t plus B into 3 m of t into cos square 2 pi f1 into t. Okay, so this is passing through a band pass filter. Now this is not a DSBSC signal, not a DSBSC signal. All these things are not a DSBSC signal. But can I write like this? 3b into m of t by 2 plus 3b into m of t by 2 into cos square theta is cos 2 pi into 2f1 into t. Okay. Now all these things are not a DSBSC signal. This is not a DSBSC signal. All these are passing through a band pass filter, not a DSBSC signal. So this is not a DSBSC signal. Now I want a DSBSC signal. Now this is a DSBSC signal. See here, this is the DSBSC signal. Message multiplied with carrier. Am I not? This is the DSBSC signal. Now if you draw the spectrum of this, now this is 2f1. This is the DSBSC signal, right? Now this is the DSBSC signal. Now of center frequency 2f1. Now what he is asking, determine the value of f1 such that the carrier frequency of DSBSC signal is 1 MHz. Okay. Now this is the carrier frequency of a DSBSC signal from the given system. Now what is the carrier frequency he is asking? He is asking determine the value of f1 such that the carrier frequency of DSBSC signal is 1 MHz. Now he says that now if this is the DSBSC signal, this is exactly the DSBSC signal FC. Now this is FC plus omega. This is FC minus omega. Okay. So here this DSBSC signal is given to generate the DSB signal with a carrier frequency of 1 MHz. Now whatever the DSB signal is given whose carrier frequency is 1 MHz. Now whatever the DSB signal which we are getting by using this system is 2f1. So can I equate these two carrier frequencies? This is the carrier frequency, this is the carrier frequency. Therefore 2f1 which is equal to 1 MHz, therefore f1 which is equal to 0.5 MHz. This is the answer. Determine the value of f1. This is f1. Okay, note down. Okay. Similar question is also available. Now question number in our classroom workbook, question number 18. Now consider a system as shown in figure below. Consider a system as shown in figure below. Now this is the system which is given to you. Now, sorry. Now this is x of f. This information which is given. Okay. Now once again I will explain the question. Read. Now consider the system as shown in figure. Now this is x of s, 10 kHz, 10 kHz cutoff frequency, 13 kHz. Now y of f. Now this is x of f. Now what is the question is determine positive frequencies. Determine positive frequencies in y of f where y of f has spectral peak. Determine positive frequencies in y of f where y of f has spectral peaks. Okay. So first we want to find y of f. Okay. Now what is a balanced modulator? I am already explaining to you. The balanced modulator is nothing but the product modulator. Okay. The balanced modulator is nothing but the product modulator because the balanced modulator output is a multiplication of two signals. But here it is in frequency domain. Given is also frequency domain. You also convert it into frequency domain. Okay. So now this is balanced modulator 1. Let us assume this is balanced modulator 2. Okay. So what is the output of the first balanced modulator? Means now this one x of t multiplied with cos 2 pi f1 into t. Assume this is f1. So what is this? What is its Fourier transform? Is nothing but x of f minus f1 plus x of f minus f1 plus f plus f1, and spectral amplitude is decreased by a factor of 2. So which is nothing but I am taking in terms of kilohertz. This is kilohertz axis. So there is no need to take again kilohertz. Now shifting. Now this x of f is shifted to 10 kilohertz. This 0 is at 10 kilohertz. Now this 0 is at 10 kilohertz. Now this is 11 kilohertz. This is 13 kilohertz. Therefore, now that 0 is at 10. Now 9 kilohertz, 7 kilohertz. Now again this is shifted left side also. This is minus 10, minus 13, minus 11, minus 9, minus 7. Okay. Now this is output of balanced modulator 1. This is output of balanced modulator 1 frequency shifting property. Okay. First you note down this. Okay. Now this is passed through a high pass filter. Now what is the high pass filter cutoff frequency? Is 10 kHz. Now the frequency is greater than, this is the high pass filter. Now this is the high pass filter. So the high pass filter will allow the frequencies greater than this cutoff frequency. Therefore this is not allowed by our high pass filter because this is the frequencies less than this cutoff frequency. Okay. Now this is what? Now this is the output of high pass filter. This is output of high pass filter. Right. Now this is the output of the high pass filter. Now this output of the high pass filter again multiplied with a balanced modulator of carry frequency f2. Let us assume this is. Now this is some P of t multiplied with cos 2 pi f2 into t. Now let us assume this is f1, this is f1, this is f2. Now P of t is Fourier transform, P of f minus f2 plus P of f plus f2. Now this is shifted right side as well as left side. Now this 0 is shifted to 13 kilohertz. Therefore, this is 13 plus 10, 23, 24, 26. Now this is 13 minus 3, 0. Now 3, 13 minus 11, 2. Now similarly left side, but left side is not required. This is y of f finally. What is the question? Determine positive frequencies in y of f, where y of f has a spectral peak, where there is a peak. Now there the positive frequencies is, now this is 2 kilohertz and this is 24 kilohertz. This is the positive frequencies in y of f. This is the positive frequency in y of f, where y of f has spectral peak. And there is no need of doing the negative side, but you can take the for practice purpose also. There is a left shift. Now this is question number 18, okay, which is simply based on the basic concept of frequency shifting property. And balanced modulator is nothing but, don't confuse, the balanced modulator is nothing but the product modulator itself. Now finally, what is the advantages of DSBSC modulation? Now tell me, with respect to bandwidth, okay, I will talking about only advantage. Now whatever the total power is carried by the sideband such that the power efficiency or modulation efficiency is 100%. Power efficiency is increased, which is equal to total power equal to sideband power. Therefore, the power efficiency is, the total power is carried by the sideband. Therefore, the power efficiency is 100%. And disadvantage. What is the disadvantage? The demodulation process is done by synchronous detector, which increases cost, complexity, synchronization is a difficult task. Now there is a quadrature null effect. There is a quadrature null effect. Quadrature null effect. All these are the disadvantages. Okay. Now, what are the main applications? The main advantage will be considered as a applications, right? Now, if you observe here, I will explain with a small example. This is the transmitting antenna and this is the receiving antenna. Now, this is, let us assume, this is the distance which is equal to 50 kilometers. Okay, let us assume. And this is the transmitted power. Now, the transmitted power which is equal to 50 watts. Now, here carrier power plus sideband power. Now, here which is equal to, this is 40 watts and this is 10. Okay. So, this is in AM. So, in AM, it requires 50 watts to cover a distance of 50 kilometers. Now, in that, carrier will take 40 watts and sidebands will take 10 watts. But if you cover the same distance, of 50 kilometers, if you cover the same distance of 50 kilometers, we just require a power of, a power of 10 watts, because whatever the total power will be nothing but the sideband power. Okay, we just require 10 watts power to cover the same distance, which is covered in AM. It will require more power, but in DSBSC require it will less power to cover the same distance. Understand not? Same distance is covered by 50 watts in AM. The same distance is covered by 10 watts in case of DSBSC. No, and some of the students are asking, if I use the 50 watt powers in DSBSC, what happens? Now we are using DSBSC, but you are using a power of 50 watts. If you use a power of 50 watts, what happens? Now, what happens is the distance between the transmitter and receiver is increased. It will cover more distance. This is the receiving antenna. Now, in DSBSC, if I use 50 watt power, then it will cover more distance. Okay, you understand or not? This is the transmitter and receiver's position. Okay, transmitter, receiver, transmitter, receiver. Okay, so what is application? With respect to bandwidth, there is no improvement. With respect to bandwidth, there is no improvement in DSBSC. So there is no specific application. There is no specific application in DSBSC. But sometimes it is used in point-to-point communication. The reason behind that point-to-point communication, but this is main with respect to bandwidth, there is no specific improvement, but sometimes it is used in point-to-point communication. The purpose is now the same distance will cover by less power. If you use the same power which is used in AM, it will cover more distance. Okay,